Prof.
Sounds good.
And
Sounds good.
So welcome back to our DDLC seminar. Today we have Professor Hespanha as our invited speaker. And today's talk title is Reinforcement Learning for Large-Scale Games. Professor Hespanha received his PhD degree in Electrical Engineering and Applied Science from Yale University in 1998. From 1999 to 2001, he was assistant professor at the University of Southern California, LA. He moved to the UCSB in Santa Barbara in 2002, where he currently holds a distinguished professor position with the Department of Electrical and Computer Engineering. Professor is a fellow of the Internet, which is IFAC, and of the IEEE. He was also a IEEE distinguished lecturer from 2007 to 2013. His current research interests include multi-agent control systems, game theory, optimization, distributed control over communication networks, also known as networked control systems, and also stochastic modeling in biology and network security. And welcome, Professor Hespanha.
All right. Thank you. Thank you. Thanks for the introduction, and thanks for inviting me to be here. Well, to be here, I'm in Santa Barbara, but to talk to all of you. But the talk is about, if you've seen the abstract, is about large-scale games and use of reinforcement learning to solve these games. So let me just show you what do I mean by game, what games I'm talking about, and what do I mean by large scale. So I think you recognize a lot of the games in this picture. Of course, you on top left there's tic-tac-toe, then there's another game called dots and boxes. If you have never come across a game where you start with a blank slate and you start putting lines, players take turns. Whenever you complete a square, you get a point. And then on the top right is a strategy game. You have to conquer some cities by moving pieces. This would not be the kind of games you'd find in a control stock or dynamical system stock. That'd be maybe a little bit surprised. The lower one would be more common in a control stock, and by the way, my background is control. It's a game inspired by a very, very classical problem called the homicidal chauffeur problem. It's a problem where you have a pursuit and the evader. The blue is the pursuer, the red is the evader. And the catch is that the pursuer moves faster, but is not very agile. And the evader is very agile, but moves slower. And it's called the homicidal chauffeur. The idea is that the pursuer is a car, and the evader is a person. The driver of the car is trying to just run over the person. And you have two versions of it on the left and right. The left version, there's a short horizon to play this game. And so the pursuer moves faster. And so the solution on the left is pretty trivial. You just aim at the evader and you go as fast as possible. Eventually you'll catch the evader. But if the horizon is short, you'll never get there. And so the best thing for the evader is, in fact, to just run away. Very trivial solution. Pursuer moves towards evader. But if the horizon is long, the evader doesn't really have a chance just to run away. And then there's a sort of a transition. And with short horizons, what the evader actually does, it doesn't try to run away because it's going to be killed if the evader does this. So in fact, the evader moves towards the pursuer and tries to fool the pursuer and goes this thing left and right, dodge the pursuer, and eventually the pursuer goes into one direction and the evader goes to the other. And by the way, everything that you're seeing here, all these games are being played optimally. So these are the optimal solutions to all these games. So even in these games in the bottom, especially if you go for the long horizon, there's a sort of a combinatorial aspect where that zigzag motion you see in red for the evader doesn't look like it's evading, but it is evading. It's basically trying to fool the pursuer into making the wrong decision. In this case, where the pursuer wants to go left or right. All right, so all the games that are here, they can be modeled by Markov chains. And in fact, that's going to be the modeling framework I'm going to use in this talk. They turn out to also be combinatorial problems. I mean, difficult, I can't say that tic-tac-toe is a difficult game just because it's small. But they are combinatorial problems, with the exception of tic-tac-toe. All of them are not trivial. And all of them are going to be, can be solved with reinforcement learning, and then that's the topic of the talk. So let me tell you, I'm going to organize the talk. My goal is to talk about games. Games are the problems where you have multiple players. In this case, it's going to be zero-sum games, so with opposite goals. But I'm actually going to start just by looking at optimization problems where there's a single player. And part of it is going to be a little bit of review of what Q-learning is. For those of you that know what Q-learning is, it's going to be a little bit perhaps boring, that first part, but it allows me to introduce particular terminology that it's going to allow me to get into the second part of the talk, is to show you what needs to change to go from a single player optimization for two-player optimization. That's the second part. And then we're going to see that there's some complexity issues. And the last part of the talk is some new results that allow us to overcome some of those complexity issues, something called opponent-based exploration. At the time you'll understand. I have there in blue sort of one of the messages here is that in general games, solving games is more difficult than solving one-player optimizations. But it doesn't necessarily have to be so. And so for the particular class of games that eventually I'm going to focus on, which all the examples before were of that class, solving two-persons game is not computationally much worse than one-player optimization. You do have to change a few things. And this is, by the way, work done with some of my students and other collaborators there at the bottom. All right, so I'm going to start with this, forgetting for a moment games, just single-player optimizations, but I need to introduce the Markov chains. I think most of you may be familiar with the Markov chain is. So Markov chain is a dynamical system. There's a state that evolves. I'm denoting the state by S. So S at time 0, S at time 1, S at time 2, etc. And at every time, there's a decision to be made, an action to be selected. That's the A's. And then what happens is that given a particular state and a particular action, that causes a transition to a next state. So it's combinations of state and actions at one time step result in the state at the next time step. In a Markov chain, in general, this transition is not deterministic. It's if I have a particular state S naught and A naught, I don't always go to S1. So typically there's going to be a distribution of states. And so this is a stochastic process. Although a lot of all the examples I've shown you before, and many of them I'm going to continue to use, this could be deterministic. It could be that this probability distribution that determines the next state based on the previous one is either 0 or 1, either probability 1 or probability 0. So that part is not going to be super important for the talk. It's going to matter a few points. Then the other aspect here, I just talked about state and actions, it's this reward. So the idea is that when you take a particular action and you have a particular state, you also not only transition to the next state, but you get a reward. And the goal here is to select the actions to make these rewards as large as possible. But the thing that complicates this is that what you want to make large is not a particular reward, not necessarily the next reward, but it's a sum of rewards. Rewards from time 0 to time infinity. And there's an expected value here because this could be stochastic, and so you talk about the average. I emphasize this business of this being the summation of rewards because in many of the games, in fact, in almost all the games you've seen before in that example, you may have to receive in the immediate future very bad rewards or no reward at all to eventually get a very high reward in the future. So for example, in tic-tac-toe is an extreme case. You don't get any reward until you win the game. It's only at the last time step when you actually win the game that you get the reward. And so this decision, these policies here that select action in terms of states, they have to be strategic. You very often have to choose bad rewards in the beginning of a game to eventually win the game or get high rewards. And that's what makes these problems difficult. Now, the title of the talk also talked about large games. So let me just set your expectations by what I mean by that. So in most of this talk, the sets S and A, the states S and A take value in finite sets. But they're typically large. And by large, I mean the number of distinct states could be in the millions, the billions, perhaps even at some point, the difference between billion and infinity is very little, at least from practical perspective. So these are the numbers I'm looking at in terms of states. I'm a little bit less ambitious in the actions. So the actions, I put them in sets that maybe tens of actions or hundreds of actions. So that's what I mean by large. Unfortunately, or even if these numbers may not seem too big, well, they are big numbers. What I'm searching for is policies. What I'm searching for, let's be specific, are functions from state to actions. So I could, in principle, if the S is take value in a finite set and the actions take value in a finite set, in principle, there's only a finite number of policies. But the number of policies, that is a very, very large number, because for every state, you have to select an action. So with these kind of numbers, if I were to ever consider enumerating the policies, the number of policies, millions to, even if I take the smallest numbers here, millions to the tens. So enumerating policy is something completely out of the question. Enumerating states, not completely out of the question. Certainly enumerating actions is completely doable. So this just set the expectations, what I mean by large scale. All right, so the way to solve this game that eventually will give rise to Q-learning, and most of the techniques I'm going to talk about, is dynamic programming. Dynamic programming is about computing this thing called value function, and the value function is an optimization. It's not an optimization unlike just maximizing this. In fact, it may seem even a little bit more difficult. This was just, I would like to pick a policy that maximizes this reward. The value function is about you, for every state, you fix a state, and fixing a state in a stochastic context, you may imagine that you just condition a distribution to a particular state. And then I want to find a policy that would make this as large as possible. So assuming that you start at that particular state and you start at a particular time t. So in fact, the value function involves solving this for different states and for different times. Now, this doesn't seem to be like a very good path towards the solution to the optimization, because I just turn one optimization, another optimization. In fact, I start with an optimization, and now I have an optimization for every state. So that doesn't seem to help very much. But let's forget for a moment about that difficulty. The interesting thing about the value function is that it allows you to do strategic decisions. So what do I mean by that? I told you a moment ago that when you are trying to solve this decision, if I want to pick an action A, I must be ready to get a very bad immediate reward, because I may in the future get very good rewards. So I have to be strategic in this decision. I cannot just look very short over a short time horizon. With the value function, though, that allows me to be strategic, because the reward I'm going to get, if I'm a particular state S, the reward that I'm going to get is a combination of two things. The immediate reward that I get, and that often can be very bad, but the value function allows me to figure out the reward I'll get after that, when I transition to the next state. And so if I do consider both my immediate reward and my future rewards, then all I need to do is to choose the action that will make the sum of the two as large as possible. All right, so if I were able to compute this value function, then I can actually be, it looks like I'm being very greedy, but in fact, I'm not being greedy, because I'm being greedy, but on the criteria I'm using for greedy considers both immediate rewards and future rewards. And so in fact, this now becomes the optimal decision. And we can show that this is the optimal policy can always be written in this way, assuming that we have the value function. Now, the value function is in general difficult to compute, but it turns out that the value function satisfies an equation called the Bellman principle, which is written here. Notice the difference. Here is the definition. Given a v, if I'm able to evaluate the right-hand side, I get the value function. Here, it looks like it's also the definition of the value function, but it's not, because it's an equation. The value function appears on both sides. So the way to think about this is a functional equation, meaning it's an equation whose unknown is the function v. Those equations are more difficult. In general, functional equations are difficult to solve. But in fact, what we're going to do is to, rather than go through the definition, we're going to try to solve this equation and find a v. And that turns out to be not as hard as you could imagine. I am in this equivalence here, saying that if you find the solution to this equation, you get the value function. There's some little technicalities that will not matter too much. All right, now this is, I just rewrote here the formula for the optimal policy as a function of the value function. This is, of course, a relatively simple formula. All I have to do is for a particular state S, I enumerate all my actions, and if my actions are on the hundreds of tens or 100, this enumeration is, I could solve this maximum by enumeration very easily. But I still have to perform a few computations that are not completely trivial. So, of course, one is compute the value function. I'm going to assume that somehow that's given to me. I'm not going to worry about that right now. But I would still then, of course, have to make this summation. Making a summation is trivial, but I would still have to compute an expected value here. There's a way that almost looks like a cheat to avoid this, which is I'm going to define what is inside the parenthesis, this expected value. I'm going to define this to be the function called q. So the function q now is just exactly what is inside this parameter. It's a function of two arguments, the state s and the action I. And if I do this, then, well, it's trivial that the same policy above can be written in this way. But the lower formula has an advantage, which is that if I were to now compute this q function instead of the v function, computing the optimal policy is trivial and I don't need to know anything about the system. To compute this expected value, I do need to know something about the system. I need to figure out what is the expect. So I have some condition on state and actions. I need to figure out for each state and action what's the probability of getting a certain S and the probability of getting a certain R. That's how I compute an expected value. So I do need to know how to compute this expected value, but the formula below, I don't need to compute anything. If I'm given the Q, then all I have to do is to enumerate all the A's and pick the best Q. And so that's the idea behind Q learning. The idea is going to be, well, if V was difficult to compute, well, maybe Q is just as difficult to compute. And it turns out that computing one or the other are of a similar complexity. So rather than trying to learn V, I'm going to directly learn Q. And then I can just use an optimal policy that doesn't need at all, no information at all about the system. So it's what we call the model-free characterization of the optimal policy. So in the next few slides down, what I'm going to focus then is how to compute this Q. It turns out that in the same way that the V satisfies an equation, Bellman principle, there's also a Bellman principle for the Q function. It looks very similar. If you were to go back to the previous one, you see some small differences. So here's a maximum of an expected value. When you look at the Q, it's the expected value of the maximum. So there's some switch here of the order you do the maximum and the expected values, but the equations look very, very similar aside from that. By the way, this type of equation is also often called a fixed point equation, in the sense that if I look at the right-hand side as an operator that operates on this function, it says that when I apply this operator to the function, I get the same operator. So this is called a fixed point equation. Okay, so the way to compute this Q is going to involve a few steps. But first, what you're going to do is to do a recursive computation. So you have Q here appearing on the right-hand side. What I'm going to do actually is I'm going to create a sequence of Qs. I'm going to start at something very simple. Let's say Q equal to 0. And it's not super important to start at 0, although it has some advantages. And then what I'm going to do is to put one element, let's say Q0 on the right-hand side here, and get the Q1 here. And I'm going to iterate this. So I'm going to construct a sequence of functions. And it turns out that if this thing was an operator, eventually this would converge to a fixed point of the operator. The technical condition for that would be that this is the most common assumption that this operates a contraction. Proving that operators are contractions are often difficult, but it turns out that for this problem they are not. It turns out with very, very mild assumptions, this type of fixed point equation, particular operator on the right-hand side, turns out to be almost always a contraction. So I'm not going to worry too much about that. Later in the talk, I'll actually have some specific conditions under which you could prove that it's a contraction, but it's fairly well known and not very difficult to prove. All right. There's still something here about this equation that's a little bit difficult to turn this into a practical algorithm, is that you have to iterate functions. So you have to start with a function, you apply the operator, you get another function, and then you get another function. And functions are difficult objects, so it would be good to somehow simplify this iteration of functions. In fact, the first thing that we do is we replace this iteration of functions by a pointwise iteration. So what do I mean by this? Essentially, this was the previous equation going from qk to qk plus 1. The whole function gets changed. What you're going to do is not the whole function gets changed. The function has values at many different states. I'm just going to, from one to the next, I'll just change the value at one state. So all that's done. So suppose I have a bunch of samples from my system. So what I mean by that, I have a state at some time tk, an action at a time tk, and then the corresponding reward and corresponding state, the reward and state at the next state. And the samples, I just random, I just get them by just playing the game. But I don't have to play the game well. I just play the game, let's say, randomly, and get a bunch of samples of state. This could be terrible playing, okay? But let's not worry about that. So I just have a simulator of my game. I play the game many times, perhaps in an absolutely terrible way, but I get samples of state, action, next reward, next state. And then what I'm going to do is, for each one of these samples, I'm going to start from an old function q to a new one. And to go from the old to the new one, I keep the value of the function at almost every s and a, except for at a particular sample. So you see here, for most of the s's and a's, the value of qk plus 1 is the same. And I apply this formula just to change the value at one particular pair SA. And I do this for all my samples. So I just change the function at one point. So the function qk and qk plus 1, they're very close to each other. You know, they're almost the same, except at one point they change. And I'm going to do another thing. If I was doing this, there was something here that was still a little bit unpleasant. I would have to compute an expected value. So what I'm going to do is I'm not going to compute an expected value. I'm going to replace this expected value that you had here by an empirical average, meaning that I would like to replace the function by the expected value of this, but instead what I'm going to do is I'm going to take the average, some weighted average between what appears here and the old value. And so this Q, what's going to do is going to do an weighted average, which eventually, if I do this enough times, it should eventually give me the expected value. Because if I average something many, many times, eventually I should get the expected value. So there are two changes to the original algorithm. One is I do very small changes from qk to qk plus 1, just one sample at a time, and I replace expected value by empirical averages. And it turns out that this, for quite a long time, is known to work, in the sense that if you do this iteration, eventually this Q converges to the definition that was various slides back, this particular definition, which was everything that you need to know to compute an optimal policy. So that's very convenient. And these results, these are some of the earliest results in Q-learning from the early 90s. One thing here, just to say, just to make the point, the reason to have this empirical average with the alpha is just if you have an expected value. If you have a game for which nothing is random, let's say like tic-tac-toe, then there is no need to do an expected value, and you could just put alpha equal to 1 here, because there's nothing to average in tic-tac-toe. Whenever you put an X on the top left, the X appears on the top left. There's no uncertainty about it. So in that case, actually, the algorithm simplifies and you can put alpha equal to 1. But if you do have an expected value, then you cannot put alpha equal to 1. You have to do some averaging. Okay. For a lot of the remaining of the talk, I'm actually then going to focus on the case on deterministic finite chain. So let me tell you what this is. So finite is, I've actually been doing this from the beginning. I'm assuming that the state S is finite, and the state where the state space S is finite, where the STs take place, and the action space A is finite too. I told you the numbers, so these were like the millions, this was tens or 100s. I'm also going to assume that the game finishes in a finite time. Games do not go on forever. That was also the case of all the games I've shown you. In my framework here, what that would mean is that at some point, these rewards become zero. So in the case of tic-tac-toe, you play in tic-tac-toe, there's really only 9 turns, if you think about it. After that, or even sometimes before that, you get 3 X's or 3 O's in a row. At that point, the game is decided, and there's no more rewards after that. So in finite time, in this particular way I'm writing things, just means that after a while, the reward is 0, so you don't need to worry about it anymore. The game is effectively over. And then it's a deterministic, meaning that this probability density function only takes values 0 or 1. So when you have a particular S and A, there's going to be one particular ST plus 1 which has probability 1, all the others have probability 0. That was also the case of all the games I've shown. So that means that you can actually take the alpha that I showed you before equal to 1. And so the Q iteration becomes actually very simple. It's just this, you take samples, you iterate, you just change the value to 1 sample at a time. And for that case, the technical condition becomes very simple to express. All you need to do for this thing to converge and eventually get to the optimal policy is you have to make sure that the choice of samples here is such that every S and A would appear in the sample. So this SC and SA here, all of them have to appear infinitely many times. In reality, they actually don't need to appear infinitely that many times. They just have to appear sufficiently large amount of times. And we can actually be quite specific in exactly how many times they have to appear. But let's just say infinitely many times. If that's the case, then you can guarantee that this algorithm is going to converge. In fact, because of finiteness, it will converge in a finite number of steps. And you could actually provide an upper bound on that. And once it converges to something that I call the limit of this, I call Q star. And if you take the optimal, if you use Q star to generate a policy, you can prove that this is the optimal policy. All right, so at this point, there were no games here, but now I need to get us into the games. Unfortunately, the good news is that we can reuse a lot of what was done before. So I'm going to be talking about what I called turn games, 2-player turn games, and they're going to be zero-sum. So let me tell you what are these turn games. I have here, it's easier to explain an example. So tic-tac-toe is a turn game because if I ever show you the state, which in tic-tac-toe would be the board position, you could tell me which player plays. And in fact, only one player can play at each state. So if I show you this particular state here, which is an empty board, we know exactly that only one player can play, which is the X player. Whereas if I show you this particular board, only one player can play, which is the O player. In tic-tac-toe, the players alternate, but in turn games, they don't necessarily have to alternate. It's not a big deal, but for example, in this dots and boxes, if you ever close a square, you get to play again. But it's still true that there are states that belong to one player and states that belong to the other player. And by belonging, I mean that in certain states like this one, only the X player can play. In other states like this one, only the O player can play. So there's a partition of the state space. Half of them, or not half, one player could own a lot more states than the other. In tic-tac-toe, it's roughly half. The players play turns. And so when you look at this picture like here, the same picture I was using before to describe the Markov chain, you still have your state, which would be maybe the board configurations. You have the actions, but now this A0, A1, A2, A3, they will correspond to actions of particular states. So if this is just tic-tac-toe, A0 is always selected by the X player, and A1 is always selected by the O player. So I can still, even though I can just call them A is not, A1, A2, A3, now there's two players making decisions, and we know exactly which player makes decisions on each state. So that's the turn, that's what I call turn-based plays. So you still have a Markov chain, you just now have some states chosen by player, some actions chosen by one player by the other, and others by the other. Now I'm interested in zero-sum games, and now in the rewards piece, things have to change a little bit. I'm going to have two players. Player one has a reward. Let's put that as a superscript. Player two has another reward. In zero-sum games, the rewards of the player are symmetric. So whenever a player gets a reward of, let's say, 1, the other player gets a reward of -1. They both maximize it, so what means that something that's good for one player is going to be bad for the other player. So reward of 1 is good for player 1, but it's bad for player 2 because it's a -1. And now what we want to do is, it looks a bit similar. So player 1 has a certain reward, J1, which comes out of rewards with superscript 1. And player 1 wants to maximize this. Player 2, because of the zero sum, is going to have exactly a symmetric reward that player wants to maximize. But of course, a large J2 means a small J1 and vice versa. The type of solution I'm seeking here, and of course the rewards that you get depends on what both players do. So this pi1 and pi2 now should be thought of the policies of player 1 and player 2. So pi1 is a policy that tells us what actions player 1 should do when player is at the state where that player can make decisions. The type of criteria I'm going to start with is what's called security. They're called security policies. And so the policy that player 1 would choose, conceptually what you do is player 1 takes one particular policy. And for that policy, the player, I'm sort of assuming here that this would be solved by enumeration. You go through, player 1 picks a particular policy, and then for that policy asks, what would be the worst policy that the other player could play against this policy of mine? So then for a particular policy, pi1 goes through all the options of the other player, and eventually we'll pick the best worst case. This minimization is a worst case for player 1, and it picks the best worst case. That's what's called a security policy for player 1, and player 2 does the opposite thing. It wants to choose the policy that maximizes, of course, J2, assuming that J1 is going to do the worst for player 1. These are called security policies. And it turns out that if you're looking for security policies, dynamic programming will work and can be defined almost exactly as for single player. If you remember when I was talking about dynamic programming, we start by computing this cost to go. We can also define cost to goes for the players here, but we define them also in this worst case way. So the cost to go from state X, S, what the player does is thinks about what are all the possible for the owned player. So this is the cost to go for player 1. It looks at all possible policies pi1. And for each one of them, figures out what would be the worst that the other player could do. And then you pick the best worst case, starting from that particular state at particular time. And then these expressions are very, very similar. It turns out that the optimal policies, the policies that maximize that worst case, can be written also as some argmax of a Q function. Of course, the policy for player 1 only matters when you're in the set of states for player 1. The policy for player 2 only in the set of states for player 2. And the Q function is defined in this way. It's more or less similar. It turns out that you can actually get away with just a single Q function that depends that is common to both players. Except that when actions of player 1 is defined in one way, when you have actions of player 2 defined in another way. And this Q function will also satisfy a Bellman-Isaacs equation. Now this equation looks a little different. It looks almost the same, except it's going to have some plus or minus signs here. The previous equation always had plus signs here. Now you have to have some plus and minus signs, and this is basically a conversion factor to figure out what's good for one player and bad for the other player. So for example, this plus and minus signs here, you'd have a plus sign if the state S and ST belong to the same player, because in that case, the meaning of the next state in some ways is the same meaning for each player as the current state. But if the two states belong to different players, you have to have a minus sign here to basically convert the value of a Q for the other player to a value of Q to my player. That is, to be honest, a relatively small detail. Perhaps much more important is to realize that the Bellman equation looks almost the same. Of course, it's plus and minus will affect the solution very much, but from a theoretical perspective or building an algorithm, it's almost the same. All right. Once you have this Bellman equation, then you apply exactly the same steps to build Q-learning. What you're going to do is you're going to replace the expected values by an empirical expectation, and you're going to do iterations on the Q one sample at a time. Of course, you have two iterations with the plus minus here, which appear in the Bellman equation. And you also get theorems that look almost the same. So for example, for the deterministic case, you can actually set this alpha equal to 1. You don't need to do averaging. And under exactly the same exploration hypothesis for every pair appears infinitely many times in the sequence, you conclude that this sequence converges and you get the optimal policies. So you can see that I was able to sort of introduce the Q turn games I spent half an hour on Q-learning for one player, and I jumped to, I basically covered the whole thing in 5 minutes for turn games. Okay, so how would this work? Well, the theory says it'll work, but now we get into this business of the large-scale games. So this works exceedingly well for a game like tic-tac-toe. Tic-tac-toe, it turns out that the total number of states, distinct states in tic-tac-toe, if you exclude all the states that cannot exist, is small. It's about 4,000. And this algorithm I just described, it's very, very fast. It will be, if you program it right in a fraction of a second, it will converge. But the other games, as you start increasing the state space, this is a different story. What you have here is a version of the dots and boxes game, 3x3. It's not a trivial game, but it's not by any stretch of the imagination a big game. But the problem is this. I've shown the game dots and boxes, at every time step you have to put a line here. If you count the total number of lines in a 3x3 game, you count that there's 24 lines. So this game will have a horizon length of 24. By the end of the 24, the game is over. What I'm showing you here now is, as a function of the horizon length, how many states exist in the game. So if you just have an horizon of 1, the total number of states is 24, because at horizon 1, one player put a line, so there's 24 lines, and there's 24 possibilities. But what this curve shows you is that by horizon 11, which is still very shy of 24, we're already in 4.5 million states. And this is an exponential growth. So now if you go back and think that the condition was that every single state has to be explored infinitely many times. Now I told you it doesn't have to be infinitely many times, just a sufficient large amount of times. You can see what the problem here is, because every one of these 4 million states would have to be explored many, many times. And I'm only at horizon 11. I didn't even reach horizon, pretty far from horizon 24. Atlatl it's a bigger game. It says even bigger state space. In fact, I don't know how to count even the states here. Well, I would know how to count, but I can't write a computer program that to terminate. All I know is that for this version here, I know it has about 4 million. But this means that, in fact, what I've shown you before allows you to solve tic-tac-toe games, but none of these games can actually be solved in any reasonable amount of time. And in fact, what they're saying is optimal play, but it was not solved using the iteration I showed you before. We have to come up with something else for games with large state space. So again, here I'm talking about millions, maybe hundreds of millions of states. All right, so now I get to the last part of the talk, which is still going to use Q-learning, but what you're going to see is that I'm going to be very judicious or very careful in my selection of samples, and that's what's going to allow me to solve these bigger games. All right, so I am interested in computing these security policies, which are this worst case, you optimize the worst case. There's another notion of policies in game theory. It's called saddle point policies. And the definition is it's not a constructive definition. This is a constructive definition. In principle, you could go, you compute the right-hand side, and you get the optimal policy. Saddle points, the definition is a test. If someone gives you a pair of policies, one for one player, the other, you say that this pair is a saddle point if these two conditions are hold. So what the first condition says is that fix one of them. Let's say fix the policy for the second player to the one there, the star one. And then optimize with respect to the first player. If the optimal is obtained exactly at the other policy, the pi1 star, then the first condition checks, true. And then you have to do the opposite. You fix the other, the pi1 star, you optimize for pi2, and you figure out that the maximum is achieved exactly at the pi2 star. So if these two conditions hold, then you have a saddle point. But again, this is a test. It's not a constructive definition. There is no way, or at least no simple way here, to construct a saddle point. If I give you a saddle point, you can check if it's a saddle point or not. It turns out that for these turn games, this is not always the case, but for turn games, security policies will turn out always to be saddle points, and saddle points always turn out to be security policies. It's a property of these turn games, not a difficult property, it's a relatively straightforward property to show. Now, there is one very different difference between these two from a computational perspective. If I were to try to compute security policies, at least according to definition, what I would be doing is I would try all possible pi1s, because I want to maximize over this. For each pi1, I consider all possible pi2s. Then I evaluate the j. So what this would mean is that if I didn't have any other shortcuts, eventually I would have to evaluate this j at number of times to be the policy space of pi1 times the policy space of pi2, because for every pi1, I have to consider all pi2s. So this will mean evaluating the j's pi1 over pi2 times. This will be policy space, the number of policies, if I were to enumerate policies. On the other hand, if I want to check this condition, what I have to do to check the first condition is I fixed pi2 star, and I just have to evaluate this at all possible pi1s. So in terms of number of evaluations of this, it would be the size of the policy space of pi1. And then if that would check, I'll do the same on the second one. So the total number of evaluations of j1 and then j2 would be pi1 plus pi2. And I don't need to tell you that there's a huge difference between a product and the sum, especially when the size of policies are very, very large. This kind of evaluation is computationally much easier than this one. The problem, of course, is that this is a test. If the test fail, well, I have nothing. But it turns out that computationally, this is so much better that it becomes possible in very large games, in fact, quite reasonable to just try things at random. Okay? So this is what policy oracles algorithms look like. So I'll give you an algorithm that will try to exploit this big difference in complexity. You start at some iteration and you pick two policies, pi1 and pi2, and you could just, you know nothing about the games, you just pick two completely random policies. Then you do the saddle point check. Basically the check that appeared here. You check this. If the check comes true, you have a saddle point and you have security policies. Now this check is relatively simple to do. If it doesn't come true, then what you do is you ask your oracle for another pair and you check again. And if the computation of this is sufficiently good and fast, then you can get away with having to do this maybe thousands of times. Because eventually this condition hopefully will come true. So this would be what sort of policy oracle algorithm would do. Now there's two things here. One is how would you go about doing this check? The second one is how would you select this oracle? And of course, I mean, for this to work, the oracle doesn't have to be a great oracle, but eventually has to, at the very least, produce the optimal policy. Hopefully, it will be a good oracle so that you don't have to do millions of iterations here. Maybe you can do a few hundreds or a few thousands. So let's start with the first condition. I'll do this check because, in fact, this is going to determine how I'm going to build my oracle. So what I'm going to do is I'm going to basically use the saddle point condition that I showed you before. So the definition was this: I have a saddle point if when I do this optimization, I get pi1 star. When I do this optimization, I get to pi2 star. Each one of these optimizations fixes the policy of one player and only looks at the policy of the other player. So these are not games. One player has been fixed. All I have to do is to minimize for the other player. And you can do this using just regular reinforcement learning. So what I've done in the first half of my talk. You have to solve it twice, and then you either conclude that's true or not for your candidate policies, the pi1k, and pi2k. And so the way you're going to do this is by using standard Q learning. Inside this algorithm, this check, you're going to use reinforcement learning twice. One to check for this condition, the other to check for this condition. So that solves this part. Then how about our oracle? Now, the trick to get this oracle to work well is to use whatever information you gathered here to improve the oracle. If you think about what's being done here, when you solve these optimizations, I take this one. I fixed pi1k and I optimize for pi2. What I'm looking here, one way to think about this is I'm looking for weaknesses of my current guess pi1k. I'm trying to optimize against it. So what that means is I am now player 2. I'm playing a player 1 does not allow to optimize as a fixed policy, and player 2 tries to beat this policy. So it's going to look for parts of the state space where this policy is not doing a good thing. If it was tic-tac-toe, it would be parts of the state space where perhaps the player already 2 X's in a row and doesn't protect against that. So what I'm going to do, sort of in words, is I'm going to use reinforcement learning here. This reinforcement learning is essentially finding weaknesses in these policies. Reinforcement learning does this by doing samples. So the samples that I gather here are samples that are going to reveal weaknesses in the policy. So I'm going to use those samples to improve my oracle. Okay, so in practice, what this means is that the oracle itself is going to have a Q function. It's going to be iterated using the typical iteration. The only difference is that the samples that I use to this iteration are going to be precisely the samples that come out of evaluating my saddle points. So in fact, this test here has 2 roles. One is to check whether or not I found a saddle point. If I found a saddle point, it finishes. If it doesn't find a saddle point, I'm going to collect all these samples and use them all to improve my oracle. So there's the double role of this check. And I'm going to use them just using the completely standard Q-learning iteration, except that using these samples. Well, what can you prove about this oracle? There's a trivial statement is that if this algorithm ever terminates, you found a saddle point. And that's true because that's the termination condition. So that part is trivial to prove. If this ever terminates, it always has to terminate the saddle point. So the thing that's not completely trivial is to prove that it terminates. Okay, so that's the thing that needs to be done. And so what we're going to show is that it's a proof by contradiction is if this would never terminate, actually the Q would converge, and so it actually has to terminate. Now, I'm not going to do the proof here, but the proof involves something that is a little bit new, which is something called a weak fixed point. So I've sort of shown you this condition before. This was the Bellman equation for the Q function. And we call this a fixed point when the function on the left-hand side is equal to function on the right-hand side. A weak fixed point is when that happens, but it doesn't have to happen over the whole state space. It only has to happen over a certain set, which I call S star of the state space, which in our games is going to be much smaller than the full state space. And that's what's going to allow us, in fact, for the algorithm to converge much faster. This set S star, the way it's going to construct it is take this Q star. We don't know if it's a good policy or not, but based on it, compute policies, pi 1 star and pi 2 star. These policies define reachable states. If you were to use these policies, you would only reach a certain set of states. That's what this S star is. What would happen if you fix the players to play one of these policies? So this S star is the reachable space under the policies derived by Q. If this function holds over those set of reachable spaces, then you call it the weak fixed point. And the theorem is that a fixed point is definitely a sufficient condition to get an optimal policy, but a weak fixed point is also a sufficient condition. But this condition has to be checked over much, much smaller subsets of the state space. And what we can in fact do is that there's a result here, which if you run this oracle, if you run the algorithm that you've seen here, you're not guaranteed that by using the samples here, you get a fixed point, but you're guaranteed to get a weak fixed point. And that's enough for optimality. So from a theoretical perspective, all the algorithms are the same. You just have to introduce the notion of a weak fixed point and then adapt the proofs for this to work. And in fact, that's how all these games were solved before. So that just so that you have an idea, even in a game as simple as tic-tac-toe, although the game has 4,000 states, the algorithm that finds an optimal solution only has to visit about half of them. Now, half is good. Tic-tac-toe is not very good. But when you look at these dots and boxes, what I'm showing you here is the number of states that need to be visited as a fraction of the total number of states for example, the 3 by 3 dots and boxes. And what this shows is that, in fact, we can find optimal policy only seeing about 5% of the states. It's a little bit funny. How can you come up with an optimal policy that will be optimal against no matter what your opponent does? And that you never explored what happens. You only explore what happens in 5% of the states. But it turns out the result says this is possible. In a way, it's because you choose policies that prevent your opponent from reaching a certain number of states. That's what's happening. That's also what's done here. The reason why I know this says this game has 4 million states is because, in fact, that's where the number of states that were explored. But I know that the game has a lot more. The game is probably on the 100 to 200,000 million states. All right, I am basically at the end of the time. Will very briefly tell you that quite a bit of what I've done can be moved to continuous infinite state spaces. And the main issue there is, how do I go about representing a function over an infinite set? And the very reasonable way to do this is by using neural networks. You put at the input of my function my state, which now can be a vector, doesn't have to be finite. And one very reasonable option to represent the function is that I have my neural network several outputs, and that gives you the function at different actions. And then the optimal policy is look at all the outputs and picks the largest one, because that's the policy are as simple as that. I have here some formulas how it go about training these neural networks. Basically, because you want to emulate this equation that I shown you before, all you do is you use this as the loss function. The loss function for your neural network is the difference between the left and the right. That's what I wrote here. You train your neural network, it goes PyTorch will do this very easily. And in fact, that's how I solve this problem, because this problem here, there is a continuous state. The players can start anywhere. And for this particular problem, actually, it wasn't a very complicated or big neural network. So you can see here, it's a narrow, like we got this to work in neural network with, I guess, 5 hidden layers. Not that many nodes, 50 nodes. And this was quite quick to get this. For this problem, in fact, almost any structure of the neural network works. It's very easy to get this neural network to converge. All right, so I am basically done here. Let me just sort of recap a few things. So I told you about Q-learning. And one thing that many of you probably knew about Q-learning, at least for one class of games, these turn-based games, the theory carries out very nicely, at least formally, we do need to change things though when we get this very large state space, because state spaces are just too big. So we've been playing quite a bit with these oracles and this thing called opponent guided exploration, which is what I told you about before. A lot of this carries over to continuous with neural network representations for the Q functions. Perhaps to finish, maybe what's more interesting is sort of some open questions. Even with what I've shown you, the system still requires lots of samples. So there's lots of things to do here, figure out how to decrease samples. Let me just offer you one option, which is easy to say, but then difficult to make in practice. A lot of these games have symmetries. If you were to change tic-tac-toe on any of the games that I've shown you, if you did a flip on the mirror or you rotated it, the game doesn't change. And a flip on the mirror means you're dividing the number of states essentially by 2. Not exactly, because some of them are symmetric. So how do we exploit that? By the way, what that would mean is that my Q function will have exactly the same symmetries as the game. So I should be able to exploit that. But in practice, that tends to be not completely trivial. I've shown you one way to build oracles. I think there's still lots of improvements here. These oracles are still not super efficient. It should be possible to do much better than that. And we have different versions of oracles than the one I've shown you here. And then the other one has to do with representation for large state spaces. Neural networks, what I've shown you before, are great because they're generic. You can apply a neural network to absolutely every game. But by exactly the same token, it means that it's very difficult to capture something specific to the game in a neural network. If I would give tic-tac-toe or dots and boxes, does one of them have better neural network representation than the other? Or are there other representations that are not neural networks that are better? So these generic representation neural networks are good in the sense that, well, you can always try them, but unfortunately, they don't exploit at all the structure of the game. So understanding how to exploit that, in particular, for example, the symmetries is, I think it's one of the things I think is most important. And at this point, I think I'll finish and just give a few minutes for questions. Thank you.
Thank you, Professor. I just have one question. Like, when you do the solving the policy, like you fix one, let's say fix pi one, and
Yeah.
then you solve for the pi two. I wonder, because you solve like how to sequentially, it's not like you don't solve it at the same time. So will this solution have some gaps?
Yeah, okay. So let me make a few comments about that. There's an interesting computational problem, which is that, in fact, if you have parallel computing, you can actually solve them at the same time. But this is actually quite important because, as you know, now you have GPUs, all computers have multiple cores. Any algorithm that you can do things in parallel is a huge win. And it turns out that's a huge win here because you can halve the time. So this is not to be underestimated. Unfortunately, in zero-sum games, there's only 2 players, so at least you can use 2 cores of your computer. The other thing you're saying about the gap, so actually it is exactly right. I haven't shown you here, but when you try to compute these 2 optimizations here, if it's a saddle point, you basically you don't get the same value for both. You get one symmetric from the other. If they are not equal, that actually gives you a gap on in principle, it gives you upper bounds and lower bounds on the values of this. And so as the algorithm progresses, you can actually make these plots and seeing this gap shrinks, which is useful because sometimes there's this notion of an epsilon saddle point, meaning you don't need to be absolutely optimal. You just want to be not terrible. And so you can actually stop the algorithm when you don't quite get zero gap, but you get small enough. So in the game like this, you may say, well, because this is a points game, I'm okay if I get within 10 points of the optimal, and the algorithm actually would allow you to do that by doing that test. The test provides you upper and lower bounds, and so you can, in a game like tic-tac-toe, the gaps are more or less trivial because it's you either win, lose, or draw, so you don't have interesting gaps. But in games with points, you get interesting gaps.
Thank you, Professor. One question from Andres. He's wondering if we can extend the result to the case where we cannot observe the game state and eventually deal with PUMDP.
That is a very, very difficult problem. There's a few cases where you can, relatively easy, but they're not super interesting. The one that's the simplest one is that it's not fully observable, but both players make the same observation. So both players have a common view of the game. Then actually the whole theory will go fairly easily because you can basically look at this observation, or in fact the history of it, as a new state, being information set. You do have the problem that in POMDPs, you can compress all the past observations just into a probability distribution, and that's not trivial, even in that case, to do. But if you think about it, in all the games where you have partial information, typically two players don't see the same thing. I mean, the classical example are card games. You see the cards in your hand. You don't see the cards on the end of the other people. And there are some ways of doing that. There's some techniques to do that. Almost all of them rely on policy enumeration. You don't search over space, you search over policies, and that would be completely impossible for these games. That's, you remember in the beginning of my talk, I told me if you ever had to do policies, the number of policies, millions to the tens, that is just impossible here. So partial information case is far more difficult, and almost all the results rely on policy enumeration. That one way or another, they have to do that. So the news there are not great. But by the way, there's lots of, I mean, if you follow the literature on that, you'll see that there's quite a community working on poker. And so there's some good poker player programs. They do rely a little bit on policy enumeration, but if you have enough compute power, you can actually still get something that's probably very far from optimal, but at least good enough to be competitive with a human player.
Thank you, Professor. Has another question. Dear Professor, are there any guarantees in more general settings with disturbances beyond the games you presented?
So there is if you had stochastic disturbances, that would be very much like could be like a Markov game. You couldn't do this alpha equal to 1 business that I was doing here because you don't have to average, but you'd have to do the actual averaging here, and you will get probabilistic guarantees. So it's this type of results that with probability better than 1 minus, let's say, beta, you get a solution that is less than epsilon away from optimal. So there's this result with alpha beta. If people have looked at some of these probabilistic guarantees, there's versions of these things which do probabilistic guarantees. Those games are computationally much worse because on top of everything else, you have to average. Right? So you have to enumerate all states and you have to average. So it is difficult for very large games. Not impossible, but difficult. So like, yeah, an example that would be like backgammon. You would play with some like that. Those are tough games.
Thank you, Professor. There has another question. It asks, when the process iterates, how much of the learning of the oracle while trying to find one set of security policies helps it find another? For example, if there are multiple.
Yes. So, okay, there's a few things to say about that. So the oracle is always improving. because the oracle keeps always getting new samples, and every new sample will improve this Q. Eventually, you actually can prove that this Q will converge. But there is one little subtlety here, which in fact is I think it's a mechanism to improve this, which has to do with part of your question too, which is, so there isn't a single saddle point. There's multiple saddle points. And this Q keeps improving, but it doesn't, there's no guarantee that the pi is actually kept getting closer and closer to a particular saddle point. So it sometimes happens, and we observe this, that the Q is starting to get close to a saddle point, but then the samples are such that it goes to another saddle point. And then has to start exploring the state space next to that saddle point, where it would be good if you'd like, let's try to stick to the old saddle point and do minimal changes. But the algorithm currently does not have a mechanism to help that. I mean, we have theoretical guarantees that says that eventually you will find a saddle point, and maybe you'll jump a little bit between one saddle point and the other. And that's a little bit of waste in terms of samples, but you eventually will find one. But we do observe that the existence of multiple saddle points, which are inevitable. I'll tell you why in tic-tac-toe. There's many ways to win tic-tac-toe. You know, your first move could be put the X on the top left. There is a policy, an optimal tic-tac-toe, that always put the X on the top left. But in fact, there is another policy that puts the first X on the top right. In fact, the first X can be put anywhere for an optimal policy. So you can see right away that this, at the very least, has 9 optimal policies. One that puts the first X. And for each one of those, there's probably many of them. So in all these games, the number of saddle points, security policies is huge. There's lots of variations on it. Anyway, so the answer maybe too long for the question.
Thank you, Professor. Just one follow-up question. Can you explain again how we figure out S star for any given problem? Also, due to iterating over policies, maybe we consider that the system could go out of S star. How do we redefine the notion of S star?
I think the Q star was in this, that's the star. I think this was the slide I had, the Q star.
Yeah, it's this S star.
The S star, right? Was it the S star? Yes. Okay. Okay. So the way is this. Now, by the way, so this is the definition. Of course, then let's do this. We don't actually in the algorithm have to compute S star. You see, there was no S star in my algorithm. This is part for the proof. So, and what we actually show is that the algorithm converges for a Q star for which the S star satisfies the condition. So that's part of the proof. Is the algorithm. There's no S star or there's a Q in the algorithm. But let me just answer specifically the question S star. So the S star is this. So this is a definition. It's a test. If someone gives you a Q star, you have to check if the left side is equal to right hand side over a set S star, and S star is built using Q star. And the construction is this. The first step you do to define S star is you compute the pi star policies. Now, we don't start by assuming that Q star has any particular. We're trying to check if it's a weak saddle point, but we can, no matter what, we can always define policies that will be sort of optimal policies if this was an optimal policy. Out of this, you get these policies. And then what we do is we figure out when player 1 fixes this one and player 2 uses any other policy, what state would be reachable? So how would we figure this out? Well, we put pi 1 star, we fix that one, and then get the other player to play random stuff sufficiently so that we explore the full state space. And then we have to do the other way. We fix pi to star and we get the other player. Now these sets, they are still big sets because you're fixing the policy of a player. Well, when you fix the policy of a player, it's very easy. For example, in tic-tac-toe, the policy could say the first X is always in the top left. All right, that's always fixed. And then you're just letting the O player do this. That actually results in a much smaller number of states because now the X player has no degrees of freedom, only the O player. But so that's how you get this S star. It's still often a big set, but much, much smaller than the full state space. And that's what we use here. Now, as I said before, we don't actually need to ever compute this S star in our algorithm. We just have to make sure that the algorithm, we have to prove that the algorithm satisfies this condition. Right? So the algorithm doesn't appear in the algorithm.
Thank you, Professor. We have one last question. Thank you for your talk. I wonder the implication of your approach to the single agent Q-learning on reducing the exploration of state space.
That is an excellent question, which I should have said. Very little. The trick I've shown you here is a trick the trick I shown you for zero-sum games. It actually is not restricted to zero-sum. It could be multiplayer games. This trick, don't have this published, but we can generalize it. But it doesn't help for single-player games because it's all about actually the key thing here is that the set S star is much smaller than S. But this set S star is obtained by fixing one policy and then letting the other player do whatever you want. With a single player, you gain very little. Of course, the fixed point condition only has to hold for games that have, for reachable states. You know, if there's a state that's never reachable, of course, then you don't care. But the big gains here are because of two players, at least two players. So what I've said here will help relatively little for single player optimization. There are other things that can do for single player optimization that we've worked on a little bit. One of them, yeah, anyway. But this is
Thank you,
sorry,
Professor.
doesn't help. That's the answer there is not great.
I just have one last question. You just mentioned about this can be also extended to the multi-agent players.
Yeah.
So I just wondering if the multi-agent player doesn't have this symmetric reward, this structure, how can we?
No, but actually what matters the most for this to work is not the symmetric part, is the turns business. So if you have multi-agents, but the agents play in turns, and it doesn't have to alternate, but what it means is that the version in multiplayer would be my state space, if you have n players, is divided into n sets. And when in set S1, only player one plays. Set S2, only one player plays. And they could then rotate, the players could play multiple times. But you have to have this business of partitioning the states in chunks, and each player plays in his own chunk. Although the zero sum actually is not the most important part here. The whole thing would have to be adapted. If, for example, you'd not be able to get away just a single Q function, then you would need a Q function for every player. But most of what I said would go through for multiplayer, for multi-agent.
Okay, thank you, Professor. It's really interesting talk. I will really enjoy it. Okay. And thank you for having me.
Well, thanks for inviting me. It's great. It's great. Thanks for all the questions. Excellent questions. Very interesting stuff.
Thank you, Professor. Bye-bye.